All right, let's get right into it. We're surrounded by all this tech that runs on electricity, and honestly, it can feel like straight up magic. So today, we're going to demystify it. We're going to break down the basic principles that power, well, everything. We're basically going to build a circuit together, right from scratch.
I mean, just think about it. Inside your phone, your car, even your coffee maker, there are these super intricate pathways, kind of like the one you're seeing now. And on these pathways, an invisible force is constantly at work. That's what electronic circuits are, and they are everywhere, quietly and reliably making our whole world go round.
So what is actually going on inside those wires, right? What's moving? What's giving it a push? And what are the rules of the road for this whole journey? Well, that's exactly what we're going to figure out.
So here's our game plan. We'll start with the basic language, then talk about charge and current, what's actually flowing. Next up, voltage and resistance, the push and the pushback. Then we'll cover the fundamental laws that tie it all together. And finally, we'll put all that knowledge to the test and analyze a simple circuit.
All right, let's start at the beginning. To really get a handle on the complex stuff, we have to start with a simple goal.
And this is it, this simple little setup, a battery, some wires, a light bulb. This is going to be our guide for everything. Seriously, all the fundamentals of electricity are happening right here in this little loop. Our mission, if you will, is to figure out exactly why that bulb lights up.
Okay, first things first. If there's something happening in that circuit, that means something has to be moving, right? So what is it? Let's define it.
So that thing that's moving, it's called charge. You can kind of think of it as a basic property of matter, just like mass. These teeny tiny particles, electrons, carry a negative charge. And when those charges start moving, well, that's what we call electricity.
Okay, so if charge is the what that's moving, then current is the how fast. Electric current is just the measure of how much charge is flowing past a point in a certain amount of time. We measure it in amps, or you'll usually just hear amps. So, pretty simple, more amps means more charge is moving every second.
Now this current actually comes in two main flavors. On the left, you've got direct current, or DC. Think of it like a one-way street. The charge just flows in one steady direction. That's what you get from a battery. Then on the right, you have alternating current, or AC. This stuff is constantly changing direction, back and forth. That's what you get from the outlets in your wall. And this difference is absolutely crucial for how we design everything from our power grids to our gadgets.
Okay, so we've got charge, and it's flowing, which we call current. But why? What's making it move? And is there anything trying to slow it down? This brings us to the two big forces in any circuit, the push and the pushback. First up is voltage. This is basically the electrical pressure. It's the push that gets the charge moving through the circuit. Think about our battery. What it does is create a voltage difference, and that difference provides the energy, the oomph, to get those charges flowing. So it's pretty intuitive. Higher voltage means a stronger push.
And working against that push is resistance. The best way to think about it is like electrical friction. Every single thing in a circuit, even the wires, resists that flow of current just a little bit. And we measure this opposition in a unit called ohms.
So now we have our three main players, right? Current, voltage, and resistance. Now it's time to learn the rules of the game, the laws that explain how they all interact. And these laws are what let us predict, design, and build literally every circuit that exists. And believe me, there is one law that is so fundamental, so important, it's pretty much the golden rule of all things circuits.
And here it is, Ohm's law. It's this beautiful, simple relationship that says voltage equals current times resistance. V equals I times R. That's it. This one simple formula is the absolute key to everything. If you know any two of those things, you can always figure out the third. It really is the cornerstone of all circuit analysis. And this graph here really shows you Ohm's law in action. See how it's a straight line? That's telling us the relationship is directly proportional. In plain English, if you double the push, the voltage, you're going to double the flow, the current. That is, as long as the resistance doesn't change. And the steepness of that line, that slope, that's the resistance. Okay, our second big law is Kirchhoff's voltage law, or KVL. The big idea here is basically conservation of energy. It just means that in any closed loop, like our little light bulb circuit, the energy you put in has to equal the energy that gets used up. All the voltage supplied by the source gets dropped or used by the components in the path. Nothing just disappears.
Okay, we have the concepts, we've got the laws. Now it's time for the payoff. Let's put everything we've just learned together and actually analyze a circuit.
So here's our circuit for today. We've got an 8.4-volt battery, and it's hooked up to 3 resistors all in a row. That's what we call a series circuit. We've got a 10-ohm, a 30-ohm, and a 100-ohm resistor. And our mission is simple. Figure out exactly what's going on in this loop.
And we're going to tackle this in 3 simple steps. First, we'll find the total resistance in the circuit. Step 2, we'll calculate how much current is actually flowing through the whole thing. And for step 3, we'll figure out how that 8.4 volts from the battery gets split up between each of those resistors.
All right, step 1. This part's pretty easy. Since the resistors are in series, meaning they're just one after another in the loop, all we have to do is add them up. So we've got 10 plus 30 plus 100, and that gives us a grand total of 140 ohms of resistance. See? Simple.
Okay, on to step 2. And for this, we get to use our new best friend, Ohm's law. We just need to rearrange the formula a little bit to solve for current. So current equals voltage divided by resistance. We know the total voltage is 8.4 volts, and we just figured out the total resistance is 140 ohms. You pop that in a calculator, and you get 0.06 amps. Or, to make it a nicer number, 60 milliamps. And just like that, we know exactly how much current is flowing through the entire circuit.
And now for the final step. We're going to use Ohm's law one more time, but this time on each resistor by itself. So for that first resistor, the voltage it uses up is 0.6 volts. The second one uses 1.8 volts, and the big one uses 6.0 volts. And now for the really cool part, what happens when you add those up. 0.6 plus 1.8 plus 6.0, you get 8.4 volts. That's exactly the voltage our battery is supplying. That's Kirchhoff's voltage law in action. The puzzle is solved. We literally know everything that's happening in this circuit now.
So there you have it. We took this invisible force and we made it totally predictable. We started with a simple question and we ended up being able to analyze a whole circuit loop. We figured out how current flows, what pushes it, and what pushes back. We've pretty much mastered the loop. But really, that just leads to a much bigger, much more exciting question, doesn't it? How do we go from simple loops like this to complex systems that can actually think, remember, and make decisions? Now that is the next step on the incredible journey into the world of electricity.